Hello. Yes, I should explain the title here. I'm claiming that we need new physics to understand consciousness. Now, when I mean new physics here, I mean something outside the physics we know, but it's not simply invented for the purpose of explaining consciousness. It's something which I think we need anyway for quite other reasons, and I'll come to that as part of the talk. First of all, there are various views about what's consciousness, what is the basis of consciousness, and the current view is it's basically, well, the brain operates according to a computer. Many people believe this, and computers are, when they get powerful enough, will do the same things that brains do, and if brains make us conscious, then these computers will be conscious, and therefore computation itself is what provides consciousness. That's one quite a common view these days. If you don't hold that view, you probably hold the next view, unless it's the fourth one. The next view, which is that it's established science, the science works so well that we have now, that in some way this science comes together and in some configurations produces consciousness. Or there's the third view that we are going to have a new or a broader view of the physical world, physics of the world, and that is what we need in order to explain consciousness. Or you might say it's nothing to do with science and something comes from outside. My view is number 3. Now I need to try to go to the next one if we can. There are many aspects of consciousness which I don't want to talk about, which most people do talk about, things like, pain or love or perception of the colour green or all sorts of things like that. I'm only concentrating on one thing, which is the concept of understanding. And the reason I'm doing this is not that I think it's more important than the others, or maybe it is, but that it's the only thing I can say anything definitive about. And I claim it is definitive, although other people may disagree with this. I'm going to point to 3 words here: understanding, and here we have awareness, and there we have intelligence. And in normal usage of the word intelligence, you would have to say an object could only be considered intelligent if it does have this quality of understanding. And if an object is not aware of anything, you wouldn't normally say it has understanding. That's just normal usage of words. And I'm going to say, therefore, that understanding is crucial to both of these things.
Sir Roger is a mathematical physicist with the eye of an artist and the soul of a philosopher. He's also a master wordsmith, capable of turning very complex ideas and making them look simple. He's also been an inspiration for a generation of physicists and mathematicians alike.
Right. So nobody's left. So I guess everybody knows that Roger Penrose did indeed receive the Nobel Prize in 2020 for physics. But you may not know that he also is the holder of OM, which stands for Order of Merit. So I'm going to do a little bit of calculation for here on the board. Chalk on blackboard. This is what we do at the London Institute. It's like kids in a candy store. This is what this is all about. So here's a calculation for you, okay? So the Nobel Prize was founded by Alfred Nobel in 1901. The OM, Order of Merit, was founded by King Edward VII around about the same time. To date, there has been 962 recipients of the Nobel Prize, of which there's approximately 120 alive right now. The OM has gotten 196 in its history, and by definition, can never exceed 24 living members. Therefore, by both measures, you can clearly see that the OM is about 5 times harder to get than the Nobel Prize.
On that
and
note,
Sir Roger has both.
On that note, can you join me in putting your hands together to welcome Nobel laureate Sir Roger Penrose, OM. But yes. One of the things that Yang and I, we agree on almost everything, but the one thing we completely disagree on is the future of AI. I'm a great skeptic, yes. and Yang is a fan.
I wouldn't say I'm fanatic, but I'm a fan.
Yeah. So in particular, sort of the role of artificial intelligence or, advanced computation, machine learning, whatever you want to call it, the role of that in enhancing human creativity. So in particular, automated, conjecture formation or creative acts, or even, as you like to think about, automated proofs. And so, some of the evidence for that is, systems. We've got a slide now about AlphaGo, and then there's AlphaZero. Right. And I think somebody in the audience here is one of the developers of AlphaGo.
Sure.
What's your sense on the role of computation, machine learning to enhance our creativity?
Oh, that's a difficult one. You see, you might explore the implications of something using a computer, which is what people do all the time now. You may have some idea about what's going on, and then you test it by computation. And a lot of physics is like that now. Sure, that's fine. There's nothing wrong with that. The question is whether you're making the computer creative. Now, what does it mean to be creative? You can certainly make it do things you hadn't thought of before. Now, is that creative? Well, I don't know. It's not usefully creative. It might by chance, you see. Well, it does this protein folding thing now, which, of course, people have found it's very good at doing protein folding. Maybe. I don't like to... See, creative is a word that's rather hard to pin down, I think. I prefer to use the word understanding. There, you see, I think it's much clearer, because you couldn't say AlphaGo understands anything. I say I have an idea about how to... This is a nice challenge. I'd like to do it sometime. To see whether... I don't know whether it would work, but you might be able to defeat AlphaGo or whatever it is, Alpha Plus, whatever these things are called. Be an interesting challenge. I won't talk about it now because I don't want too many people to think of it ahead of time. But it is a way that... sure, it beat the world champion, but that's in the normal way you play Go, which starts with an empty board. So the idea would be to modify the game a bit. You see, the thing about making a very good Go player, that it's very clear what the aim is. You can tell who wins. So you can make it play itself a zillion times, and without understanding a damn thing, it can play itself a zillion times. And it knows which one wins, when it wins. And so it's clear what wins means. Now, it would be very different if you have something which is not clear what the objective is. If it's got a clear objective like that, then maybe, yes, you can make a computer do it better than a human being, which is what happens with Go. That's right. But does it understand what it's doing? I think one could make a case that it doesn't. But I'd like to that's a challenge which I had in mind using. Now, I had this thing with chess, which you could do that.
Right. But there's a growing community within the mathematics community who are sort of saying that, this analogy of mathematics being like chess, and this community thinks that we can, within the next few decades, AI, or the likes of AlphaZero, would start proving theorems and raising new conjectures in mathematics that are better and faster than us. So what do you think of...
It's possible. You see, I'm not arguing against that, really.
Okay.
I'm just saying it doesn't understand what it's doing.
Right. So even though it's produced a correct proof of a correct theorem?
Yeah, sure. Well, there's examples of this. The four-color problem. There's a proof. I used to waste a lot of time on trying to prove the four.
Right, I see.
The four-color problem is proved. I believe now there is no proof at the moment which doesn't at some stage use a computer.
Exactly.
Now, does that computer have the faintest idea what it's doing? No.
I see.
Do we know why that calculation gives you a proof of a four-color problem? No. And not unless you follow the argument. What is following the argument? You've got to understand it. You've got to know what it means. Now, it doesn't mean that you can't take advantage of having the computers. That's what people do, and that's what they're for. But the question here is maybe it would find something, some clever little thing that nobody's really thought of, and a proof of it, I suppose. I don't see that's impossible. It's a bit sort of... Well, there is a thing which... There's a little joke in one of my books. I don't know if anybody's seen it yet. I can tell you the joke, yes.
Please.
There's a picture, I think it's in Shadows of the Mind, yes. There's a picture which is illustrating this understanding point, where it's got a picture of all our ancestors doing all sorts of wonderful things. There's in the foreground, you see the mathematician who's trying to prove a theorem. Okay. And he's completely devoted to try and prove this theorem. And there's a saber-toothed tiger just about to pounce on him and eat him up, you see. So what I'm trying to say is that's not selected for. What is selected for is these people who build a wonderful mammoth trap. And you see the poor mammoth getting rather disturbed. He's about to fall into the trap. And you can see people building shelters in the distance and growing crops and domesticating animals and using their understanding. And that's why the concept of understanding with this universal quality was selected for. And consciousness was something which was developed in human beings. Nothing purely for doing mathematics and seeing how to do theorems which can't be proved by simple axioms and things like that. Now, there are examples like this, and I give this in the book. I think I do in that book. I can't remember what's in the book now. But anyway, what I'm trying to say is that the quality of understanding is something which uses consciousness. And understanding is something which is very broad in its applicability, and it has a very, very essential role to play in mathematics. Now, the example I think the Goodstein example is in Shadows of the Mind. That's a very nice example. You can explain to people who don't know very much mathematics, and it's a thing you can't prove by ordinary induction, which is, you learn that in school, how to prove, you can prove something is true for all n. And the way of doing it is using mathematical induction. But the Goodstein theorem is being shown you can't prove that by mathematical induction. Yet we know it's true. Now, how do we know it's true? Well, we can't have done it by, maybe these ancestors of ours could have formulated the idea of mathematical induction. But they can't have thought, what's the use to evolution of thinking of transfinite induction? That's what Cantor did. That's what you need to prove the good science. You need transfinite induction. Okay, you can understand. You don't have to be Cantor to understand it. You don't need the genius of Cantor. Maybe he was a fluke and somehow could think of this. No, you just follow the argument. And you say, I see, that works. Yes, it's true. Now, how do we have the ability to see that when the algorithms, if they were just algorithms, that we use to develop our abilities, well, in fact, were just algorithms. We have to have something beyond algorithms which enables us to understand things. Now, I'm not saying that won't be achieved by future technology. I'm glad that I won't be around when that future technology comes about. But sure, there might be some, as I say, a latter-day Frankenstein who can create a conscious being. Maybe it can happen. But it's not just by computation. You have to take advantage, according to me anyway, take advantage of whatever is going on in this part of physics that we don't understand yet, which is the collapse of the wave function. And somehow nature has done it already by itself.
So I've read early on, as a teenager, your first book up there, Members in Mind. And then more recently, this year I read your second book, where you sort of Shadows.
Yes. Right.
I find these books more relevant today than ever before. I mean, so many people are debating, and I've had so many of these debates, and we've had these debates about the sort of brave new world of what could happen. And I find it's one of these little miracles to see that argument, to know that we know truths which are non-algorithmic, right? Cannot be done on any sort of computing device.
I had this view that whatever understanding is, and what it is something which needs consciousness to whatever. I mean, consciousness, there's all sorts of other things I know, of course. You know, the perception of the color green or something like that. These are conscious things. But one of the things consciousness does is to understand things. And understanding is therefore, I formed the view, not a computational procedure. Now, nobody believed me. But I was thinking, I didn't think of doing anything with that. But much later, I thought perhaps when I'm retired, old and retired, I'll write a book about it. And then Stephen Hawking was writing his book on brief history of time. And then I heard some people talking, this was Marvin Minsky and Edward Fredkin, and they were talking about how wonderful computers were and the ones in the future would supersede anything we can do. And I thought, well, I can see where you're coming from, but I don't believe you. So I tried to write The Emperor's New Mind, and in the process, find out what it was in the brain which could be non-computational. Well, I believed from the Dirac talks, actually, that it had to be, I was just in the process of elimination. It couldn't be Newtonian mechanics, it couldn't be general relativity, it couldn't be ordinary quantum mechanics, I understand it. It had to be something missing from the theory. And what's missing is this thing called the collapse of the wave function. I don't know how much you wanted to ask me about this, but I did form that view that there was something missing in Dirac's talk. It made it clear to me. But he wasn't trying to emphasize the talk. It was more the following. He was getting to the point. He's talking about quantum mechanics. And you can have, in quantum mechanics, you can have a proton can be here, or it can be here, or it can be here and here at the same time, in different ways, here and here at the same time. Then he took out a piece of chalk and he broke it in two or something. My mind was wandering. I was looking out the window or something. I don't know what he was saying. When my mind came back to what he was saying, he moved on to the next subject. So I thought, why on earth can't a piece of chalk be in two places at once? If I'd heard him, he probably would have said something to calm me down and stop me worrying. But I didn't hear him, or I didn't remember, so it stuck with me all the time. There must be something in quantum mechanics which goes beyond the Schrödinger equation, which goes beyond the framework of... I didn't know much until much later that Dirac thought exactly the same thing, but I only learned that much later. Schrödinger thought the same thing as Dirac too, as did Einstein, but many people thought that quantum mechanics is all the answers. But I thought, no, there's got to be something else going on, which is called the collapse of the wave function. And then I tried to write this book, The Emperor's New Mind, to find out enough about how the brain works so I'd see where this comes in. So I read about neurophysiology and I found about a Hodgkin-Huxley nerve transmission, and I thought there's no chance in hell. The signals as they go down the nerves disturb the environment too much. You can't preserve a quantum coherence like this. So I hadn't any idea at all. So I kind of fudged the way out to the end of the book, saying something about quasicrystals, and maybe there's a similarity there. I don't know. Well, maybe there is, but I didn't really believe what I was saying at that point. But then I got lots of letters. I thought it would be nice to have lots of letters from young people doing their research, and that would be nice. What did I get? Lots of letters from retired people. These were the people who had time to read my book and write about it.
Well, speaking of letters, I mean, there was an open letter by Elon Musk and Hawking on challenging the singularity. I mean, this possibility of the singularity, technological singularity, not your singularity.
Oh.
And there was
this
open letter about the rise of we're doomed to failure.
Yes,
so you're a big skeptic of this, obviously.
Yes, but you have to be careful about what I'm a skeptic of. You see, it's not a computer. It's not in that sense. It doesn't mean that we might not someday, that some latter-day Frankenstein will see how to incorporate the right structures and make a conscious being. I don't say that's impossible. I just say it's not a computer.
Oh, I see.
But you see, the argument is that you have to incorporate the collapse of the wave function in an active way. And I couldn't see how neurons did it. Then one of the letters, which wasn't from an old retired person, it was from Stuart Hameroff, who was a neurophysiologist, but mainly he was his job was to put people to sleep. So he was name's got out of my head, an anaesthetist or anesthesiologist, as they call it in the States, and that was his job. But not like most of his colleagues who just wanted to make sure they were able to wake the people up afterwards and they didn't cause them pain, things like that. But Stuart was really interested in what on earth is he doing when he's putting them to sleep. He also emphasizes the wrong term because it's not sleep. They're unconscious, but it's not really sleep. It's something different. But his view, which he'd formed for quite different reasons, that it had to do with these little structures called microtubules. And he wrote them to me, and I thought, oh, not another letter from a crackpot, you see. And what are these things he's talking about? These microtubules, what are they? So I looked up. Oh, he's right. And they were beautiful symmetrical structures, I thought. And so there's a much better chance. Here you might be able to preserve quantum coherence at a level which could perhaps preserve coherence. You see, you need to have a quantum state which remains undisturbed, doesn't leak out into the environment, coherent in a certain way to such a level that when the collapse of the wave function happens, it happens in a way which is usable. So the idea was, and we formulated this idea that we call orchestrated objective reduction. You see, it's not just the collapse of the wave function, because that's happening all the time, but it's got to be orchestrated in a way and made use of by the microtubules and by structures in the brain. And that's the scheme that we've been working on for.
But what about matter and space-time curvature at very tiny scales? What about space-time curvature of quantum particles? Now, Roger Penrose came up with this idea in his book, The Emperor's New Mind, in 1989. And he started by, to make it simple to draw something, three-dimensional or four-dimensional space-time in two dimensionals in these space-time sheets. So 3 dimensions of space along what would be the x-axis sort of are condensed to 1, and time along the other axis. So a particle, as we see here, is a curvature in this two-dimensional space-time sheet. And if the particle moves, as it does in the bottom, the curvature moves. So you can think of this as representing an oscillation of a particle between two different locations, purely classical. Now, what about superposition? Roger realized that if this were the case, that superpositions were actually separations in fundamental space-time geometry. You had a curvature over here and a curvature over there, and the particles, as you can see on the right, are in two different places at the same time. So this was an approach to explain quantum superposition using general relativity, which, as I said, is a unique trick in and of itself, because the two, general relativity and quantum mechanics, have been irreconcilable for all these years. And this is at least a conceptual approach. So here's the idea again. On the right, you see the quantum superposition of separated space-time curvatures with the particle in two locations at the same time. Now, you might imagine that if this separation were to continue, we'd have multiple worlds. One curvature would go off and form its own universe with its particle. One curvature would form another, and each would evolve its own universe, and we have the multiple worlds. But Roger Penrose suggested that these superpositions and separations in space-time geometry are unstable, and they will self-collapse or undergo objective reduction due to an objective threshold at a time t given by a very simple equation, basically a form of the indeterminacy or uncertainty principle, where the time t is h bar over E sub g, where E is the gravitational energy of separating the space-time from itself, or the mass from itself. And here was the kicker, along with a moment of conscious experience. Now, this came from a long argument through Gödel's theorem that I won't go into, but it turns the Copenhagen conscious observer approach 180 degrees, upside down. Instead of consciousness causing collapse, collapse causes consciousness. So this was an amazing and quite courageous proposal. It was a big slap in the face to AI, who was saying that consciousness is a computation. It tied together general relativity and quantum mechanics, and it was a hypothesis for a mechanism, an actual specific mechanism for consciousness. And 28 years later, it's still the only mechanism that has been put forth for consciousness. We heard about Tononi's 5, but that's kind of a correlation. Emergence, a lot of hand-waving stuff. But really, this is the only specific mechanism that's ever been proposed, this objective reduction. So here it is again. The separated curvatures evolve, and that at time t, one of them ceases to exist, the other one is selected, and bing, a moment of consciousness happens. Now, this would be occurring everywhere, like decoherence, in the random environment, in the floor, in the chairs, in the clicker, in the tables, but randomly, and these events would be essentially what we would term decoherence. I don't think decoherence actually exists. I think objective reduction, you'll pardon the expression, trumps decoherence and replaces it, probably even a better term. And so there is no such thing as decoherence. So decoherence would spread, but it would reach this threshold and self-collapse. So these would be proto-conscious, or like Whitehead's simple occasions of experience. And metaphorically, they would be like the notes, tones, and sound of an orchestra warming up, each musician playing his or her instrument. It's a cacophony. It's noise. What we need for consciousness that we have, the kind of consciousness we have, is something to orchestrate this noise into something more like music. How could they be organized or orchestrated in the brain, for example, for full, rich, conscious experience? Roger needed a quantum computer in the brain which could orchestrate quantum information, halt or terminate by this objective reduction, connecting to space-time geometry, and be influenced by non-computable Platonic values. This was another feature he added, which is kind of like following the way of the Tao or divine guidance or something along those lines, as well as reaching qualia, awareness or feelings, and would be in a position to regulate functional, neuronal, and synaptic activities. I suggested to him microtubules. At that point, I had been studying microtubules for 20 years. To make a long story short, we hooked up. Here we are at the Grand Canyon after the first Tucson conference, and we developed a theory based on microtubules. And here's a picture of a neuron inside of which are microtubules. And Chris showed a slide of a cell as kind of a minestrone soup of things floating around. That's not how cells are. They have an ordered structure due to the microtubules, which seem to process information. And on the left, you see a microtubule, which is a cylindrical lattice of proteins called tubulin. And microtubules do a lot of things. They guide motor proteins and synaptic plasticity due to the placement of tau proteins. And when they disassemble and the tau falls off, we get Alzheimer's disease. So microtubules can process information. I spent a lot of time modeling information processing in microtubules and then later quantum computing in microtubules with Roger. For example, we calculated that the E sub g of 10 to the 16th superposition entangled tubulins, about 1/10,000th of the brain, would reach threshold in about a 10 millionth of a second, 10 million times per second for a conscious moment. So not just one microtubule, but many entangled throughout the brain. And basically the idea is that this can happen at different frequencies, and moving from left to right, we're going faster and smaller inside the cell, into the microtubules, into the quantum realm. And on the far right, you see that this is where anesthetics work. We had a paper in Nature Scientific Reports last year showing that anesthesia dampens quantum vibrations in microtubules to selectively erase consciousness. There's evidence for this from the work of Anirban Bandyapade showing experimentally quantum vibrations in microtubules in terahertz, gigahertz, megahertz, kilohertz, and hertz. So there's experimental evidence for this, for quantum vibrations in microtubules. So the basic idea is that there's a threshold is reached, there's a bing moment in the microtubules in the brain connected to fine-scale structure of space-time geometry, as you see at the bottom. So that other bing should be on the far right, and consciousness is a sequence of bing moments. It appears continuous, like a film or video appears continuous, but it's actually a sequence of discrete frames or events. And here's that sort of the hierarchical multi-scale scheme again, from the cortex down into the individual quantum events. And if we go to the right further, faster, we're going to get into the structure of space-time geometry and may not even need biology anymore. That the information in consciousness is occurring at this level of fundamental space-time geometry, which goes all the way down to the Planck scale, which you see on the right, where there's information and patterns and so forth. And it could be that consciousness extends into the structure of the universe at a deeper level. Bing, 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 bing. Kind of like astral projection in Vedic philosophies and so forth. Or in Eastern philosophy, where bing is everywhere, and the self would be a mega bing, you might say. Atman from Brahman or something like that. Or consciousness leaving the body at the time of death. When the blood stops flowing, the oxygen stops being delivered to the microtubules and other structures, the quantum information doesn't dissipate, but can leak out, but remain entangled as something like a quantum soul. I'm not suggesting any evidence for this. Many people have. I just think there's a scientific explanation for it if it does occur, which I hope it does, and I think it does. And certainly, scientists can't exclude it outside of the brain, consciousness outside of the brain, until we've proven or know what consciousness is inside the brain. Now, a couple things about scale in the universe. If this is a log scale going from left to right, from large to very small. The far right, we have the Planck scale. On the far left, we have the whole universe. And consciousness or biology at the microtubule level, for example, is almost smack in the middle of this on a log scale, which means it can have leverage in both directions or be influenced in both directions. I think this is kind of interesting. Raises the question in the universe, when did consciousness arise? Was it fairly recently with tools and language, earlier with animal cells, earlier with all life, or before the universe began? Now, most people would say that the universe began at the Big Bang. Roger, who likes to buck conventional wisdom, wrote this book, The Cycles of Time, where he suggested that rather than the Big Bang being the beginning, it was actually preceded by another eon, which in turn was preceded by another eon through something called conformal rescaling. And there's now evidence for this in concentric rings in the cosmic microwave background, which appear to represent giant black hole collisions in the previous eon that form these concentric rings and can be seen now in the cosmic microwave background. There's been some initial evidence, and more evidence is coming from that. So it's kind of interesting. Raises the final point. The finely tuned universe is the concept that the values of fundamental physical constants are precisely what are needed for life and consciousness to occur. The anthropic principle encompasses explanations for this finely tuned universe. If things weren't exactly the way they are, we wouldn't be here. Why is that? Well, the things that have to be right are called these dimensionless fundamental physical constants, and I won't go through them, but there are 22 numbers, and if they weren't exactly what they are, we wouldn't have stars with light, we wouldn't have life, and we wouldn't have consciousness. So how did we get so lucky? This is the anthropic principle question, and there's two types of answers. The weak anthropic principle suggests we won the cosmic lottery. We exist in the one and only universe of an infinite number of parallel universes able to support consciousness. Selection bias. We are the only ones able to ask the question. So there's the multiple worlds, and only one of them supports consciousness. We won the lottery. The other possibility is the strong anthropic principle suggests that life and consciousness play some intrinsic role in the nature of the universe by influencing these constants which are somehow embedded in space-time geometry. How could that happen? One view is God. People say God started the universe, perhaps. The other possibility is that these fundamental constants mutate and evolve with each eon transition from eon to eon, with each Big Bang to the next, tuning and driving the universe. The universe itself is actually evolving and mutating from eon to eon, like a rebirth of a human, reincarnating, you might say. And consciousness could be the optimizing factor. So presumably there was consciousness in the previous eons, as we see on the right, and perhaps with each transition, the properties, the fundamental constants, are being tuned to optimize consciousness in the next eon. So over eons and eons, the universe is evolving to optimize conditions for us to be conscious. So if we make it through this eon, the next one will be even better, hopefully. So let me conclude by saying that consciousness consists of self-organized rearrangements, ripples, if you will, in the fine-scale structure of the universe. We're actually tied to the universe itself, amplified through quantum vibrations in the microtubules and other structures in our brains. These ripples, each a wave function collapse due to Penrose objective reduction, are orchestrated and connected to the brain by quantum vibrations in microtubules. And I think consciousness is more like music than a computation. And self-organizing music. You don't necessarily need a conductor, but some more like jazz or improv or something like that. 3, consciousness may be guiding evolution of the universe over eons. As I said, the universe itself is reincarnating from eon to eon. And finally, I didn't talk about this, but microtubule vibrations, if they're responsible for consciousness, are a viable target for treatment of mental and cognitive disorders. Now, we know microtubules have vibrations in megahertz, and in 2013 we published the first study showing ultrasound into the brain improved mood in normal volunteers. I was the first guinea pig. I can tell you it does work. We've since shown improved mood, and others have shown improvement in Alzheimer's symptoms and pathology and brain trauma in animals. So I'll end there, and thank you very much for your time.
Physics, the condensed matter physics, which happens at the ultra low temperatures, how does that apply to this level of quantum?
Oh, you mean in the brain is not ultra low temperature?
Right,
Great.
yeah.
Sure. Now, well, I mean, when superconductivity was first discovered, you had to have extremely low temperatures, and it was thought to be a process which only existed at very low temperatures. And then high temperature superconductivity was discovered. Okay, not quite at the level of a brain, but if you consider the whole scale of possible temperatures, it's up there almost. So I think the more we discover, the more we find that phenomena which we believe can only exist with very simple or very cold systems, that when the structure is, we don't always understand it very well, but we see events, circumstances under which these phenomena, which seem to exist only theoretically at first, only very low temperatures, are playing a role at much larger temperatures. Now, I think I refer to experiments which did require very low temperatures, but that's really the beginning to see that these phenomena are there at all. And the current view of quantum mechanics, if you look at the sort of view of what people think amongst physicists as a whole, they tend to think there can't be anything wrong with quantum mechanics. It's such a wonderful theory that you don't expect to see violations of the type I'm talking about. But the theory itself is self-inconsistent, as I tried to describe. I mean, the evolution of the quantum state, the Schrödinger equation, is something inconsistent with what happens when a measurement is made. And it's sort of driven physicists crazy trying to understand that. And people attempt also to apply quantum theory to circumstances which are extremely different from the very small things we have observation for. For example, black holes. And people talk about the black hole paradox, information paradox, which is something that comes about where somehow you destroy information in a black hole and yet you couldn't because a quantum system can't destroy information. And so this is regarded as a great paradox. But you're looking at a huge thing on the one hand, and to believe that the quantum mechanics that we hold to today is going to stretch to that level without change seems to be an enormous assumption. And particularly because there is this evidence in the very way we use quantum mechanics, the two processes, as I tried to point out, the quantum evolution according to the Schrödinger equation on the one hand, and the process which seems to take place when measurement is made when the wave function collapses on the other hand. And people have worried about this for decades, and usually they don't think that quantum mechanics can be wrong because it works so well in circumstances under which it does work and explains lots of things which weren't understood previously. But it's not the whole story, and we need to look beyond theory as we have it at the moment, and I don't think it's going to last in its current stage. My prediction is these experiments will show that quantum mechanics isn't quite right. This will be a big step. I think it's probably a minority prediction, but it's certainly what I expect.
If I can comment on that question, there's a phenomenon called Froelich coherence. Herbert Froelich was a biophysicist in the 60s and 70s, and he proposed that if you have biological molecules in a geometric array, and he referred specifically to membrane proteins in a membrane. So they were constrained in a geometry, and they were oscillating coherently due to voltages in them, that they would oscillate coherently due to the heat bath. Ambient temperature, the heat surrounding would pump them, and they would oscillate coherently. And this has actually been shown in systems recently. And I met Froelich in the 80s, and I asked him if microtubules would also be good candidates, and he didn't know about them, but when I explained them to him, he said yes. And so kind of what we're talking about of the coherence among tubulins in a microtubule and microtubule is kind of a form of Froelich coherence. I think, didn't your brother work on something like that with Onsager?
Well, he did work with Onsager. I'm not sure he worked on liquid helium and things like that, where you have very cold temperatures and you have behavior which certainly people thought would only exist at very low temperatures. And sure, it's a challenge. I think this is one of the reasons people have trouble with the point of view that Stuart and I are putting forward, because it does require that you have quantum coherence at a very high level compared with what people can do in the lab. But the more I learn about biology, and I'm still very ignorant about it, the more I'm impressed by the extraordinary kind of effects which take place, which do seem to depend on quantum effects. And of course, we have a long way to go, because, as was commented earlier, on the fact that what we need is not just quantum effects in the brain, but beyond quantum effects. That is to say, that consciousness, we claim, is taking advantage of where quantum mechanics isn't quite right. So that's a bold thing to say, but I think we have good reason to suggest such a thing, but I can also understand why there's a lot of opposition to that view.
We need the quantum coherence to get to Roger's new physics. So that comes first. And when we started, people were skeptical and worse than that. But then in 2006, plants were discovered to have photosynthesis, and it's much briefer, but it's a much shorter path length.
Quantum effects, they were discovered.
Quantum effects in plants. So if a potato can do it, our brains can probably do it.
All right, so that was very kind of you both to give us this discussion, and thank you all for your patience. There is, I'm told to let you know that there's some food and drink outside on the terrace, and thank you very much.